Alright, so in this section we want to do a couple of problems where we're going to be doing molecules, number of molecules to moles. So we're going to use Avogadro's number within this section. When we have questions of this nature and we're going from molecules to moles, we're going to want to use our number 2 conversion factor. We're going to want to use Avogadro's number over the mole, or 6.02 times 10 to the 23rd molecules in 1 mole. And so for this one, we don't need to calculate the molar mass because the molar mass is not in our conversion factor. So even though Avogadro's number is very big and it's a pain to work with, at least we don't have to calculate molecular weights. So we want to know how many molecules are going to be in 0.25 moles. So what we want to end up with is molecules. That's what we want. We're starting with moles, and so we just need our conversion factor in here. So our conversion factor is number of molecules over moles in this case, because that's what we want to find. So molecules has to be on top. So I'm just going to abbreviate molecules, molic. And this is going to be over 1 mole. Right? So if we just calculate this out, our moles are going to cancel out. And our answer should be left in number of molecules. So let's go ahead and calculate this out and see what we get. And so we end up getting about 1.5 times 10 to the 23rd. And this would be molecules of CO2. In fact, it could be molecules of anything, really, because it's just dealing with Avogadro's number. So 0.25 moles is essentially 1.5 times 10 to the 23rd of anything. Alright, let's do our problem down here on the bottom. So now in this question, we've got how many moles are in 8.4 times 10 to the 25 molecules of water. So in this case, we want to end up getting moles, and we're starting out with our number of molecules. So when we want to calculate this then, we're going to want to use our same conversion factor that we used in the first problem, only this time we want moles on top because that's what we want to calculate. So we'll have 1 mole on the top and we'll put Avogadro's number on the bottom. So we're going to see our molecules in this case are going to cancel out, and our answer is going to be left in moles. So if we calculate that guy out, and the answer that I get when I calculate this out is 139 moles. So you probably round that up to 2 significant figures, which would be 140 moles. Alright, and we don't leave it like this. We have to say it's moles of water. So there's one other interesting thing that we can do with Avogadro's number. We can actually use it to calculate the number of atoms inside a specific molecule. So let's go back and take a look at our example from our last problem of looking at potassium phosphate. Okay, so for this type of equation, if we have a problem that says something like, how many atoms of oxygen are in 1.2 moles of potassium phosphate? So we're going to have to do some relationship work here, because right now we're given moles of potassium phosphate, and so we know we can do a conversion between moles and molecules, which we want to end up getting to. We want to end up getting the atoms. But if we look at our moles, this is going to have to go moles to molecules of potassium phosphate first. And then we're going to have to figure out how to change our molecules of potassium phosphate into just the oxygen atoms. So in our final answer, we want oxygen atoms. So that's what we want to know. So now we need to start out with what we have. So we're starting out with 1.2 moles of the K2HPO4. So we can convert this to number of molecules by saying there's 6.02 times 10 to the 23rd molecules in 1 mole. right? But this is going to give us molecules of K2HPO4, not of our oxygen. We need one more conversion factor to help us get all the way to oxygen atoms. So in that, we're going to learn from our equation that's up here in the top. We know for every one molecule of K2HPO4, how many oxygen atoms are there going to be in there? So we can write a separate conversion factor based on the number of atoms that are present. So we know one molecule of these guys contains 4 oxygen atoms. Right? And that's what we want to end up finding. So we're going to need to use this relationship here. Maybe oxygen wasn't such a good one to choose. Oxygen, that's not a 0. Okay, so we're going to use that conversion factor here too, and we want molecules of potassium phosphate on the bottom so that they cancel out, and we'll be left with our answer as oxygen atoms. So this is going to be times 4 oxygen atoms over 1 molecule of K2HPO4. So if we put this all in line, we can come out with our number of oxygen atoms. And so if we do that calculation, we would end up calculating that there's 2.89 times 10 to the 24th oxygen atoms in 1.2 moles of potassium phosphate. So we can utilize and carry out individual number of atoms within a specific molecule by using our ratio of how many atoms per molecule that we have. And so we can do one extra conversion step and we can calculate that out. So this represents looking at our molecules to mole conversions.